Okay, good morning. My name is Mackenzie Woodman. I'm the application specialist here at Spectral Evolution, and today we're going to be talking about one of our common geological applications, which is porphyry copper deposits, and talking about them from a spectral perspective. So I'll go over who Spectral Evolution is and how our spectrometers are used in the field, in the core shack, and in the lab for geological applications. So like I said, we'll introduce spectral evolution, then we'll talk about porphyry copper deposits and alteration types, and then talk about EasyID and how our software can help you in your geological applications. So spectral evolution has been around for nearly 21 years, established in 2004. We're located in Haverhill, Massachusetts, and we're built here as well. And we're the leading manufacturer of high quality UV-Vis, NAR spectrometers and spectroradiometers. And today we'll be talking about spectrometers. So our common applications are in hyperspectral applications, remote sensing and vegetation, mining and geology, as well as photonics and calibration transfer. So the first thing I want to do is introduce what a spectrometer is and how it works. So a spectrometer or spectroscopy is the study of the electromagnetic spectrum as emitted or reflected by various materials. The electromagnetic spectrum is a representation of electromagnetic radiation, and they're defined by their wavelength. A reflectance measurement directly relates to the material's chemical structures and bonds, and our spectrometers typically are full range from 350 nanometers to 2500 nanometers. So a spectrometer reads the radiation with a radiometric calibration, and it can measure the amount of energy that's coming from something, or the amount of light. For a spectrometer, which is going to be collecting reflectance percent, that will measure a white plate, which is a 99% reflector across the electromagnetic spectrum. It'll use that as a reference, and then it will calculate a ratio between what amount of light bounces off of a white plate and what bounces off a material to give you the chemical structures and absorptions of any given material. So that's how reflectance percent is used and how a spectrometer uses it. So what differentiates different spectrometers is our different spectrometers is their spectral resolution. So we have our oreXpress, which is a standard resolution in the industry. This is common to many other it's high resolution. It's common to the industry, and it's our lowest resolution instrument. So that'll have a 2.8 nanometer resolution, an 8 nanometer in the Viz, an 8 nanometer in SWIR 1, and 6 in SWIR 2. Our oreXplorer is a high resolution, a new standard for the industry and geological applications. This will have a 2.7 nanometer resolution in the UV-Vis, a 5.5 in SWIR 1, and 5.8 in SWIR 2. And then we have our oreXpert, which has our highest resolution, or is the highest resolution for field-based instruments on the market today, which has a 1.5 nanometer resolution in UV-Vis, 3 in SWIR 1, and 3.8 in SWIR 2. So for all of your really hard to differentiate minerals, the oreXpert is the best option for you. But for most applications, an oreXplorer's resolution is excellent for differentiating different minerals without ambiguity. So all of our instruments are designed to be used in the field. As you can see here, we have it in a backpack, scanning rock samples that have been collected and they're made to be used in the field. They've been ruggedized, and they have no moving parts, so that with repeated use in the field, we see very rugged performance and little need for maintenance. They're also designed to be used in the core shack, so that would be less strenuous on the instrument, but can still be rolled around on a cart and things like that. So they're designed to be used portable with a portable battery. And this is our contact probe, which we'll talk a little bit more about later. But they're also made to be used in the lab as well. So what we're trying to do is bring lab quality data into the field, into the core shack, and in the lab. So this is a highlight of our benchtop probe. This has a tungsten halogen light source inside of it with a sapphire window. And what we do here is it has trays for powdered samples. So if you have any samples that are powdered and you want to take a reflectance measurement consistently off of it, we can pack these trays with that spring mechanism that will make sure that you have good repeatable data from your benchtop probe. So this is the least portable of our accessories, although it can be portable on a cart and things like that. And then we have two kinds of contact probes for different size class that you're trying to take a reflectance measurement off of. So we have the contact probe on the top left. That would be our 10 millimeter contact probe. So that would be a 10 millimeter spot size diameter. That's for general applications on rocks and rock samples. And then for very fine grain or something that you're trying to target with less surface area, and all these surface areas are going to be a perfect average due to our optical design, will be a 3 millimeter spot size on our mini probe here on the top right. And that clip on the bottom is actually our white plate. So that will clip off and then clip onto the front of the contact probe in order to take a white reference measurement. So it's nice and convenient for field use. Oh, both of those also have tungsten halogen light sources to give you high energy across the entire spectrum. So now I'm going to talk about what we came here for today, which is porphyry copper deposits. From a spectral perspective, I'm going to give a general overview of how our instruments are used in this industry and how they differentiate different minerals. So minerals as system indicators. Clays and phyllosilicates occur in hydrothermal deposits like porphyry copper. Spectral signatures, each mineral or many minerals have unique elemental wavelength features. For example, muscovite shows a strong absorption feature at 2200. And on the right here, we have a figure of different minerals with different absorption features and unique spectra. So geological implications are composition reflects hydrothermal fluid characteristics like temperature, pH, and chemistry of the deposit. And for exploration, plotting spectral data helps map alteration zones and system position quickly. So all of our instruments are made to quickly collect data, and then our Darwin software helps you collect that data and do some data processing for your given application. And then EasyID will help you identify minerals using regressions and things like that. So porphyry copper alteration and the key concepts. Why identify alterations? They indicate proximity to mineralizations and provide info on the fluid temperature, pH, and chemistry of those deposits. So identifying alteration assemblages is key to understanding porphyry copper systems. Proximal zones near the core typically show potassic alteration with K-feldspar, biotite, and anhydrite formed under high temperatures and acidic conditions. Moving outward, sericitic zones with white micas dominate, and at greater lateral distances, propylitic zones and chlorite and epidote indicate more rock buffered near neutral fluids. And advanced argillic alteration So forms under acidic conditions during vertical fluid ascent. So using a field spectrometer, this helps geologists quickly identify these assemblages in the field, also in the core shack and in the lab, improving the system modeling and vectoring towards mineralization if you're trying to find and mine these minerals. So phyllosilicates and or clays are present in most porphyry-related alteration assemblages, and white micas, the aluminum OH wavelength shifts can be used to map gradients in hydrothermal fluid compositions, pH and temperature, like we said before. So here I have just a diagram of some of the different bonds that we look for and spectral features that we look for. So we have a white mica chlorite and then white mica and chlorite, and you can see that they have these unique spectral features for differentiating, and use a spectral geologist will be able to use these spectra to try to tease out what position in the geologic features that you're in. So alteration minerals from the spectral perspective. So now I'm going to go through all of those different alteration zones and talk a little bit about how they're used. So one of the key discoveries is the recognition of a sodic calcium alteration assemblages that form at depth. This assemblage is characterized by albite, actinolite, epidote, and chlorite with possible additions of titanite and garnet. Typically develops where brine has been drawn into the system. From an exploration standpoint, identifying these minerals in core is significant. It often means that you are positioning below the main mineralized system or possibly just adjacent to a more prospective zone, missing the upper parts of the alteration package. Spectrally, these minerals have distinct absorption features, making them straightforward to detect with high-resolution field or core spectrometers. Recognizing this pattern early can help refine interpretation and vectoring towards mineralization quickly. And then we have a potassic alteration zone. So this involves the addition of potassium and iron at the expense of calcium, often seen with feldspars and biotite veining, sometimes with magnetite and anhydrite. Epidote can also occur in these systems, while feldspars are not SWIR active and require complementary methods for detection. Spectral data from a field spectrometer is valuable for identifying associated minerals. In particular, epidote composition in a potassic setting differs from that in acidic and propylitic zones, and spectral analysis can help distinguish these variations. So a lot of these applications, our spectrometers will be used in concert with a lot of different other methods for geological applications, and many of the people in this webinar probably know that well, but these are meant to be part of a suite of lab instruments. Many of the mineral identifications can be done with our instruments, but some don't have the spectral features in our range, and so some mineral samples may need other methods. So in propylitic, so now talking about propylitic alteration, alteration is characterized by hydrous mineral assemblages, often dominated by epidote and influenced by fluid temperature, depth, and oxidation state. Carbonates and sulfur are also common outward in the system. You may see hematite, dusting, or reddish halos around these zones. Identifying these minerals with a field spectrometer provides valuable clues, determining the orientation and extent of a propylitic halo. And then for sericitic phyllic alteration is a hydrolytic assemblage marked by the formation of muscovite, often fine-grained and referred to as sericite, commonly associated with the ore-bearing mineralization. These zones typically occur within a few hundred meters to about a kilometer from the ore body. Tracking this assemblage is also crucial for vectoring and seeing where you are, and monitoring the spectral shift at the 2200 nanometer feature, which indicates changes from muscovite to sericite to illite. So 2200 is nanometer feature is very important for this identification. So intermediate and advanced argillic alteration often overprints other zones, so understanding your position in the deposit is critical. Spectrally, kaolinite and dicite are tracked using a 2170 to 2220 nanometer feature for intermediate argillic zones. In advanced argillic settings, key indicators include alunite composition shifts at 1480, 1495, and pyrophyllic features, which signal high temperature conditions. These spectral markers help confirm advanced argillic alteration and its associated acidic or high temperature environments. So to summarize, porphyry copper alteration halos have distinct spectral features that can be mapped using hyperspectral field spectrometers like the oreX series. These tools track key minerals such as alunite, kaolinite, pyrophyllite, and critical 2200 nanometer sericite feature, which can indicate proximity to the ore body. They also help monitor temperature and compositional changes in epidote chlorite measurements, and these measurements take just 3 seconds, or on average about 3 seconds to take. So they're very quick to collect a lot of data. Saving and data analysis can be very quick using our EasyID software. So this saves time and cost compared to traditional assays and complementing other exploration methods. So our instruments are very valuable on a site and in an application like this. So as far as high resolution spectra and EasyID, this is our EasyID software. So here we have some spectra from porphyry alteration. And so what we can do here, and what I'm really trying to show you, is we have the mineral scalars on the right. This will give you values for some of the alterations and bonds that, or features that we have at those particular wavelengths. And in the middle of the screen, you see those green zones. So what you can do with that is target specific spectral features while you're running your regressions and your match regions. So you can adjust the match regions, slide them around, create different sets of these match regions for different minerals, which will help you match up to spectral libraries. We have a host of different spectral libraries that are available, but you can also develop your own if you have known materials and are looking for something in particular, or have lab data on different rocks. So you can add those into existing libraries or complete your own libraries as well to run regressions. And you can do different statistical analysis on these. So you can look at them in first derivative, convex hull quotient, and things like that, where you can quickly identify different correlations with different statistical approaches. So you can also collect hundreds of samples, load them into EasyID, and have it log all of your matches and batch process. So you can analyze hundreds of scans and have it give you, with match regions that you've given it, the top 5 matches for different scans. So it's very useful for mineral applications and for geological applications. So I would also recommend looking at one of our last webinars, which was spectral analysis part 2. We'll talk about most of our features within EasyID, and I would recommend exploring some of our other webinars where we go into more detail on how to use EasyID and how useful it can be. So thank you very much for your time today, and I'd be happy to answer any questions via email or yeah. So thank you very much.